right? So you're responsible for being able to do all of those because they might come up. But if you really just want to sort of concentrate on 2 questions, knowing that I'm going to grade one of them, I gave you those 2. So, okay, cool. All right, so any questions? Otherwise, we'll just go over all of that tomorrow.
So for the number 2, you wanted us to draw the trees. Okay, got it. You told me that you wanted to bring it up in class.
Oh, thank you. So yeah, this business of derivation trees. I'm close to getting a new laptop. So derivation trees, we never like formally talked about, but I kind of alluded to them. So let's just take a look at question A here. So we've got the vocabulary, terminal symbols, production rules. Our start symbol is S, and we want to show that BC/BBA is something recognized by this language, right? So the idea is we're going to start with our start symbol, and that's going to transform into BCS, right? And we know that an S can also change into a pair of B's followed by an S. And we know that S can also change into an A. So BC/BBA should be part of our language. So one way to represent that is to say, okay, so what's a part of our language? Well, S is definitely part of our language, but it's not comprised of terminal symbols. But S is also a BC followed by an S. And an S is also a BB followed by an S. And an S is also an A. And if you look at it like this, these leaves, right, BC/BBA, that tells you a set of symbols in order that makes up a word in your language. So that's what we consider to be a derivation tree. It's showing that this will let you derive this, right, or BCS or BC/BBS or any of these others. So it's just a way to sort of show which of these production rules you use in which order to get to a particular string. So, other questions? Number 4. Recognizes the string 1001. So recognition is not too bad. There's a bit of an ambiguity in here, though. So when we talk about recognizing a string 1001, there's 2 ways to do this. There's an ambiguity in 250, right? Certainly, if the input is this, we want to recognize that. If the input is, oh, thanks. If the input is 1001, that's going to be recognized. If the input is something like this, which eventually has a 1001, is that still going to be recognized? And if the input is something like this, which started with a 1001, but then had some extra stuff, is that still going to be recognized? Or if you have right, so here was a 1001, so that's certainly recognized. But also here's a 1001, so should that string be recognized? And we haven't really said what to do one way or another, so for this case I would leave it up to you. But let's take sort of the most simple way of interpreting this. let's just find when the input contains a 1001 and say we'll recognize that. So here's one state. This will be the initial. And if you have a 0, then we haven't found our first symbol yet, right? If you have a 1, we can go to a state which says we've seen the first character. And then if you have a 0, we'll go to a state which recognizes the 1, 0. And a 0 will take you to a 1, 0, 0. And a 1 will take you to a 1, 0, 0, 1. And there's a recognized state. And if you get a 0, oh, so sorry, if you get a 1, 1, right, we might go back to our initial state. And if you're expecting a 0 and you see a 1, we can go back. And if you're expecting a 0 and you see a 1, we can go back. And if you're expecting a 1 and you see a 0, we can go back. And let's just make it sort of straightforward and say whether you have a 0 or a 1 will stay in the recognized state. But there's still some wiggle room here, right? So this is supposing that, well, I wouldn't do it like this, but I would accept this if I didn't give you other instructions. But in reality, if you've got a 0 and then a 1, and then a 1, 0, 0, 1, we should recognize that, right? So if you've seen your first 1, and then you get another 1, that should probably take us back to here. And similarly, if you've got a 0, yeah, that should stay over there. Those are okay. So if we label these, S0 means waiting for a 1. S1 means we got a 1. We need a 0. S2 means we got a 1, 0, and we need another 0. S3 means we got 1, 0, 0, and we need a 1. S4 means we got the whole string. Mm-hmm. So yeah. So all right. Let's do it right. So here's our initial state.
You said you wouldn't quite do it like this. Is there a better way?
Yeah, we're going to do it right here. So certainly if you're waiting for a 1 and you get a 0, we're just going to hang out. If you're waiting for a 1 and you get a 1, we'll go to S1. Okay, at this point you're expecting a 0. If you get a 0, we can proceed to the next state. But if you get a 1, let's stay right here and say that 1 might be the beginning of a 1, 0, 0, 1. So here, if we get a 0, we'll proceed to our third state. But if we get a 1, let's go back to S1. Because S1 means we got a 1, we need a 0. So 1, 0, 0. And here, if you have a 1, we're recognized. If you have a 0, then we got to go all the way back to the beginning. Because if we didn't match our pattern here, now we've got to wait for a 1. And that's what S0 says.
So if you wanted to accept the 1, 0, 1, and then like another, like that top right one you have there, the example number.
This one? Oh, this.
Yeah. From S4, would you then, if it's a 0, go back to the beginning, if it's a 1, go to S1, and then have to keep taking in?
So if I get a 0 from here, I could go back to S0. If I get a 1 from here, I could go back to No, if I want to accept this,
No, yeah, you go to S2.
so a 0 could go to S2, a 1 would go to S1. Yeah. But we'll do the easier. So 0, 1, 0, 1, 0, 1, 0, 1. I think that's everything. Figuring out what the question's asking is a lot harder than actually coming up with the answer. All right, other questions?
With Turing machines, do we always assume it starts on the first non-blank character?
No. There's no built-in assumption where the tape begins, but usually we specify. But it's an interesting dilemma because let's say we have a tape and it's got some binary and then it's got blanks all the way over. And we don't know where in this tape we're beginning, right? Can we actually find those numbers if we don't know if they're sitting to the left or the right? Like all we know is that somewhere on this tape there's a series of 1s and 0s. You could go right forever and you might be going in the wrong direction. But is there something else you could do? Well, what if you're sitting over here and you're already sitting over a blank?
You could have it go in whatever direction you're going in, and every time it hits a blank, change state. Once you get to like a certain amount of states, change directions.
Okay, but there's no limit to how far over you might be from the number.
You could make a thing go right one way and then left two.
There you go.
And right three.
Yeah.
And that would make you,
Is that guaranteed to find your number eventually?
eventually, if you had a way to know what it was.
Yeah, it's a countable number of positions on the tape, even though it's infinite. So if we start off, move to the left 1, move to the right 2, move to the left 3, move to the right 4, eventually, wherever the number is on the tape, we're going to encounter it. It's a kind of inefficient way to do it, but I think it's the only way to do it.
Require an infinite number of states.
No, I don't think so.
You could just cycle from like 1 up to like 5, and then go back to 1.
Well, the other thing you can do is you can leave marks for yourself on the tape. Since the tape's blank, you can move left until you get to your marker, and then move right. Right, so start off by putting a mark, say here and here. So move left till you get to this mark, and then change it so it's 1 spot to the left, and move to the right until you get to your mark, and change that so it's 1 spot to the right, and now move left till you get to your mark and keep going back. So you don't need to record how many steps you're taking. You're putting a mark down on the tape that tells you you should reverse direction, but before you do, you move that mark further out. And eventually, your marks will look like this, and when you get to this mark, right before you move it over, you check to see if there's a number, and if there is, now you found your number.
Is that how that website you were using works when it does addition and multiplication? It sets aside.
It certainly does something to find out how big the numbers are, right? And it does put down those temporary marks here and there. But I've never taken apart that algorithm. I've never tried to write one myself. I've done addition, and that's not too bad. But I've avoided that sinkhole. You had a question?
Yeah, for number 8, you asked, like, can it keep a track of how many net 1s and 0s?
Yeah.
Have, like,
So recognizes a string that contains the same number of 0s and 1s. So what did we think about this? Yeah, you said no. How come?
Because it would have no way of keeping track of how many zeros
Yeah, you'd have to use a different state each time you encounter an additional 0 or 1. And if there's no limit to the number of zeros and ones, then there's no limit to the number of states you need. And that one makes it feel like you'd need an infinite state machine. So I don't think you can do that, although now this Turing machine thing has me wondering if there's a trick. But no, this has an infinite tape, so.
Is there a way of knowing what a Turing machine is capable of? Because we were talking about how we compare computers to that.
Yeah.
How do we know what that is capable of?
It's a good question. It's capable of a lot of things, but there are some things it's not capable of. We'll talk about one of those shortly. But I don't know what I mean, there's a definition of computability which you can take to mean computable on a Turing machine. So it's almost the definition of what's computable is, can it be done on a Turing machine? But it's a really interesting question, I think. And I don't know a non-cheating way to answer that. But we'll see something that you can't do with a Turing machine, which will be interesting. Congratulations on your math competition. High score. That was very cool. Other questions? All right, well, let's think about computation. So we've talked a little about order of complexity here and there. We're talking about it more in 222 these days. But remember, there's this notion of order of complexity, roughly how quickly a problem's complexity grows as you increase the size of the problem. And we use this when we're doing things like storing and retrieving information or sorting information. And bubble sort, which we're doing in 222, remember, was an order n squared. And so if you have 10 times as much data, it takes you 100 times as long. That's pretty unpleasant, right? But it's still not as bad as some other things. Now, order n cubed is even worse. Some matrix operations become n cubed. And order n to the 1000th sounds pretty horrifying. But all of these things are extremely preferable to, say, order 2 to the n. And eventually, order 2 to the n is going to be bigger than order n to the 1000th. Okay, this is a really, really frightening growth rate. It's doubling the amount of computation when you increase the problem size by 1. And this is even more frightening, order n factorial. Yeah, and I'll give you a classic example. This is called traveling salesperson. So here's the idea. We've got a set of cities. And there's a distance from each city to, could be every other city, might not be, but we'll say it is. And you know, these distances never work exactly like geometry says they should. I missed some, but don't worry about it. It might be distance of, 20 from this city to that, and it might be a distance of 30 from this city to that, but there might be a highway between here that takes only a distance of 45. And so the faster way to get from here to here would be to use this route instead of doing a 20 and a 30. And so all these paths have different distances on them, and here's the question that traveling salesperson asked, suppose you have a particular city you're beginning at. You would like to design a trip which, starting from here, travels to every city at least once and returns with the smallest total travel distance. Right? Very, very simple question to state. Just minimize your travel distance so that starting from here, you can get to every city and come back to where you started. And we can brute force this very easily because starting from city A, we have a choice. So let me name our cities. These are glorious names for cities. So from city A, we could choose to travel to either B, C, D, E, F, or G. We have 6 possibilities. For each of those, we then have 6 possibilities of where to go next. If we choose to go to A, our next city could be A, C, D, E, F, or G, and so on. And we can add up the distances as we create each of these paths, and at the end of this, we'll have all the possible paths explored, and we just pick the shortest one. But if we assume that there may be some reason in traveling from A to B to come back to A, because maybe from A to F is going to be a lot shorter than B to F, right? Then if we have n cities, or let's say n plus 1 cities, then our first move we have n options. Our second move we have n options. Our third move we have n options, a total of n times. That's actually n to the n possibilities, which is much bigger than n factorial. Because n factorial is like 100 times 99 times 98 times smaller things. 100 to the 100th is 100 times 100 times 100 times 100. Right, that's even worse. And traveling salesperson is order n to the n if we do the sheer brute force approach. And that's really unfortunate if your job is sales and you travel. Because that's a huge growth rate. Right? Think about how n to the n grows from n equals 2 to n equals 10. It grows from 4 to 10 billion. And it gets a lot worse, a lot quicker. So here's a standing question is, for a given algorithm, how efficiently can we solve, for a given problem, how efficiently can we solve it? What's the most efficient algorithm we can come up with? There's better versions of a solution for traveling salesperson. And there's statistical approaches. If we want to find our shortest route within a certain percentage, we can do a lot better than this exponential growth rate. But if you want to find the best path, the shortest total path, right, you still got to do a lot of work. And we differentiate between these cases up here and these cases like this. So these, we say, can be done in polynomial time, because n to the 1000th is a polynomial. So what's a polynomial in n? It's n raised to some power times some constant, plus n raised to a smaller power times another constant, plus n raised to another smaller power times another constant. And we waved our hands the other day and said that those smaller terms don't matter and those constants don't matter. So if we can find a polynomial of degree 1000 that represents our complexity, we can just say it's O of n to the 1000th, or n cubed, or n squared, or whatever. So these are considered polynomial time algorithms if you can do it with complexity n to some number. Okay, but not like n to the n. That's not a polynomial. That's not a polynomial. That's not a polynomial. These are worse than polynomial time. Much worse.
That's the technical term for it.
Yeah. So we make this distinction between problems that can be solved in polynomial time and those that cannot. So if a problem can be solved in polynomial time, we say that it's a type P problem. But what do we mean by solving it in polynomial time? Solving it with what kind of machine? with a Turing machine. So this is part of what Turing machines are good for, is for analyzing the efficiency of solutions to problems. So if we can solve a problem in polynomial time on a Turing machine, it's a type P problem. Okay, there is another type of polynomial of a Turing machine, which is called a non-deterministic Turing machine, or an NDTM. Non-deterministic Turing machines are much faster than regular Turing machines. They're faster because they contain inside themselves a genie. Okay, there's a genie that has great wisdom and foresight and can answer questions for you. Thanks. And can answer these questions that a regular Turing machine cannot answer. So what's the nature of this genie in a non-deterministic Turing machine? A non-deterministic Turing machine, you have your state table. If you're in this state and this is your input, then write this on the tape and go to that state. But there's multiple possible states that you might go to. It's no longer deterministic. Knowing you're in this state and this is your symbol does not tell you exactly what your next state will be. Your next state could be here, or here, or here, or here. Okay, there's an ambiguity as to what your next state is. It's not deterministic. Now you can think of it as the next state being effectively random from the states that you've listed as possibilities for your next state. The machine randomly chooses one of those states. That's the non-deterministic point. But here's the wrinkle. It's not really a random choice. The genie inside the machine always makes the best possible choice to get you to an answer. Okay? So if you're in this state and this is your input, go to either state 1, 3, or 7. The genie will decide which of those states you should go to get closer to your answer. And it knows magically which state you should take. Now, if you don't like genies, you can think of this in terms of parallelism or parallel universes. When you get to one of these places where you might go to one of 3 different states, the machine forks off into 3 copies of itself. This machine goes to the first state, this machine goes to the second, this machine goes to the third. And each of those continues until it gets to the next branch where it might go to one of multiple states, and the machine splits off into copies. So all the possible branches that you might make are being evaluated simultaneously. Okay, but the genie's doing this in its head, presumably. But you could have a quantum computing, multiple state, non-coherence kind of setup, whichever you prefer. Okay, what does this do for our efficiency of algorithms? It lets us solve a lot of problems more efficiently. So, for example, consider traveling salesperson again. And let's phrase this as a yes-no question. We can ask the question, is there a path shorter than 300 that gets me from A to all my cities back to A? Okay, if you can answer these yes-no questions efficiently, you can answer the whole traveling salesperson question efficiently. Because start off with a number that's way too big, right? Just add up all the paths, or pick one path, right? And say, is there a path shorter than 519? If it says yes, ask, is there a path shorter than 518, 517, 516? As soon as it says no, you've found the shortest path. And that's going to take order, whatever it takes to answer that yes-no question, times however many times you ask the question. So it's some fixed number, the sum of the path lengths or something. So if we could answer the yes-no question efficiently, we can solve TS. So how do we answer a yes-no question? Well, if you have this genie in your machine and you say, is there a path shorter than 519? If there is, the genie tells you which branch to take so that when you come back to A, you've gone less than 519. And you come to a state where it halts, meaning I found a path less than 519. And if it can't find a path like that, it'll halt in a different state, meaning I was not able to find a path shorter than 519. Well, if the genie knows exactly which way to go at each city, how many steps does it take to find your path that's shorter than 519, it takes however many cities you have minus 1. All you got to do is say, okay, well, let's see. Let's go here, and then here, and here, up to C. We'll go down to E, over to G, and back, add them up. Hey, it's a shorter path. It took 6 or 7 operations, or however many cities you had. So on a non-deterministic Turing machine, this is an order n operation. And if you have a total road length of 1,000, right, it might take you 1,000 times order n to answer the whole question. That's still order n. So on a non-deterministic Turing machine, traveling salesperson is order n. Now, we don't have an algorithm for solving TS in polynomial time on a regular Turing machine. So it's not class P that we know of. But on a non-deterministic Turing machine, we can solve this in polynomial time. That puts it in a special class. So a class called NP, which means solvable in polytime on a non-deterministic Turing machine. So the P is actually poly and the N is actually non-deterministic Turing machine. So NP does not mean not polynomial. Okay, NP means it is polynomial on a non-deterministic Turing machine. And there's lots of problems we can solve in polynomial time with this genie on this non-deterministic machine. But things like TS have eluded a solution in polynomial time so far. We have not been able to find an algorithm that works in polytime, but we have not been able to prove that there is no polytime algorithm on a regular Turing machine. It's an open question. And it turns out it's a huge open question. And it's a huge question because of this concept called NP completeness. So some NP problems are called NP complete. And basically what it means, if a problem is NP complete, it means you can take any other NP complete problem and change it into any other NP complete problem in polynomial time. So NP complete is a class of NP problems that effectively are all the same question. You can take the solution to one and use that to get the solution to another in a polynomial amount of time. Okay, what does that have to do with anything? Well, so here are some examples of NP complete problems. So most of these, I have no idea what they even are. Click problem, click cover problem. Those are uninteresting. Graph coloring is fun. Hamiltonian completion, we're going to talk about Hamiltonians in a while. Minimum spanning tree we'll talk about. Bin packing problem, knapsack problem, and several variants. Traveling salesperson problem, bottleneck traveling salesperson, all of these things. Partitioning, solving two variable quadratic polynomials over integers. So solving that kind of equation. Subset sums, we talked about those. Closest string. Battleship Bejeweled, Candy Crush, Donkey Kong. Here's the good stuff, right? All of these, Legend of Zelda, and Metroid. All of these are somehow relatable to each other. If you could solve one of these in polytime, you could solve any of them in polytime. Because in polytime, we can change Metroid into Legend of Zelda into Lemmings. And if we have a solution for TS, we could change any of these into TS in a polynomial amount of time and then solve the TS problem. I don't know. And I wonder what part of Pokemon they're considering. right? So this is a partial list of NP-complete problems. Yeah. Uncapacitated facility location, sure. I believe that. So here's the thing. If you can find one NP-complete problem that you can solve in polytime, you can solve all of these in polytime. So the long-standing question is basically whether P and NP are the same thing. And this is one reason people are so anxious to try to find a polynomial time solution to traveling salesperson, because it's one of the easier problems to pose. And amateur mathematicians, computer scientists, whoever, are constantly working on this and coming up with proofs one way or another that you can or can't do this. A lot of technical journals put limits on how many papers you can submit per year on traveling salesperson, because they just get so flooded with minor tweaks on someone's previous submission saying, like, I think I solved TS, right? It's a very hard problem, and the general majority opinion is that this is not true, right? P is not equal to NP. We cannot solve TS in polynomial time on a regular Turing machine, mainly because if you could do this, so many other problems just suddenly fall. It's also very frightening to certain entities, because if you can do this, you can do things like factor large numbers into primes, which kind of kills your whole crypto system right there. And all these other things just sort of fall apart.
It's like, so, proving one NP problem, does that, NP complete problem, really prove that you can do all of them?
Yeah, that's the nature of NP completeness. Right? To be in the category NP-complete means that a solution to any other problem in that category basically gets you a solution to that problem. Basically meaning after a polynomial time amount of work. Now there are NP problems that are harder than this, that are outside of this realm, but
Does that mean it's like the same algorithm, or how?
no, there's some way that you can get from one to another though, and I don't understand that part of it. Like I say, this can be a big sinkhole that like you fall in and you never come out, which isn't a bad thing. Yeah. So it's a standing question, and there's these Millennium Prizes, and I think it's $1 million standing prize for answering this one way or another. But there's a whole lot more at stake than just $1 million, although that would be kind of cool. Like, do your 215 homework and get $1 million for it. Nothing wrong with that. All right, so that's an open area.
How would you prove that there isn't a solution to it?
That's a really, really intriguing notion, isn't it?
Because, I mean, like, you can prove a solution isn't valid.
Right.
I guess you'd probably have to expand from that to say all solutions.
And you can prove that you have a solution.
Well, yeah, that's just, I have a solution.
Yeah, you plug in and show it. But how do you show that there's no solution possible? To me, this is one of the really kind of mysterious aspects of mathematics. But let me give you an example. I may have talked about this before, but I never get tired of talking about it. So there's a quadratic equation, order 2 polynomial in X. And if we know the values of A, B, and C, we can find a solution for this, correct? If we allow complex numbers, we can always find a solution for this, even if the square root has a negative thing inside, right? We can say our favorite. I'm pretty sure when I'm old and senile, I'll be mumbling that, and hopefully people know what I'm saying. So what about cubes? Is there a cubic equation? There is. I'm not going to write it down because I don't know it. But there is a cubic equation, and how about quartics? Is there a quartic equation? There is, and it's even harder to write down than that one. It's bigger, and it's more of an algorithm.
Oh yeah, because there's going to be like 4 solutions.
Yeah, there's always 4 roots. And it's easier if you say, you know, this equals that, and this equals this other thing, and this equals this, and then x is equal to these. But you could spell it out. So what about a quintic, 5th degree polynomial? Is there an equation for that? It's never been found, but it's actually been proven that there is no such equation. There is no general formula for the solution to a 5th degree equation. And to me, that's like proving there's no solution to TS in poly time. How do you prove that you can't be very clever and come up with x equals blah, 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 and you plug in A, B, C, D, E, F, and there's your x? How do you prove that there's no equation that satisfies this? And the proof that this is impossible, that there is no general solution to the quintic, was done by an 18-year-old in France, long time ago, centuries ago. And his name was Galois. And if you've taken classes with me before this, you've almost certainly heard me talk about this. I touch on it in 120 sometimes. And he came up with a few new branches of mathematics and used them to prove that there's no general solution to the quintic. And he died long before anybody understood what the heck he was talking about. He was haunted by misfortune throughout his life. He applied to an academy and his application was lost. And he would send a manuscript in and someone would be reviewing it and they would die and the manuscript would be lost. And he just constantly felt like the world was working against him, and it seemed to be. He was eating lunch in a bar, and this was in France, and it was around the time of a French Revolution, and somebody was talking politics, and he said, you know, I've been thinking about this, and he started waving his hand, but he was holding his fork and his knife in his hand, and people thought he was calling them to riot, and so a big riot broke out. And when the police came and they said, who started this? They said he did, and he ended up in jail for a while. Just all these horrible things, right? And then he apparently got involved with a woman who was also involved with someone who was a really good shooter and challenged Galois to a duel and, you know, honor French, that kind of thing. So he agreed to duel him. Well, Galois had never shot a gun as far as anybody knew, and he was facing this expert with a gun. So it was going to be a duel in the morning. Well, he stayed up the entire night before doing an all-nighter, writing down all of his mathematical theories, which he got written down, but then, you know, of course, he got shot in the duel and he died a few days later from infection. And that was the end of his life. But quite some time later, somebody found his notes. And I think it was a few decades after this, people started to study them seriously and piece them together, and discovered that this was not only legitimate mathematics, it was novel and it was brilliant. And in amongst there was a proof that the solution of this equation cannot exist, along with the idea that if you use a straight edge and a compass, so just a straight edge with no marks on it and a compass, you can do all kinds of things. You can take an angle and cut it in half. You can bisect an angle. You can take a line and you can draw a perpendicular to it. You can do all these little constructions. But there was a standing question, can you take an angle and trisect it? Cut it into three exact angles that are all the same. And the same thing he used for this proved that there's no way to trisect an angle with a straight edge and compass. Right? Not that we're not smart enough to do it, it's impossible to do it. So this is an area called field theory. Yeah, totally. And this has to do with something called field extensions. And it's a beautiful branch of mathematics, and it came from who the heck knows where, right? I mean, it came out of the mind and heart of this 17, 18-year-old, but where it came from before that, no idea. But it gets you these limits on what we can or cannot do with our mathematics, which to me is like a whole different area of reasoning. So that's what pulled me back into math after like a decade away from it, was trying to understand this and this. And it's a really cool area. Say what? Oh yeah, yeah. I have a book in my office, which is the one that I used when I decided to learn this. It's about this. The subject is abstract algebra, and you want to get through finite field theory and looking at field extensions, and then it gets you into something called Galois theory, and that's what all of this comes from. And it's if you understand everything that comes before it, it's a pretty small step, but just a whole bunch of these small steps, starting with the preliminaries of abstract algebra. But for me, it was a really good relaunching point into mathematics. I think it's pretty cool stuff. So, but anyway. All right, so tomorrow we will continue the weirdness, and we will look at limits on what a Turing machine can do. And here's the basic question we're going to work with. A Turing machine, remember, if you go to a state that isn't defined, or if you can't find a state with a corresponding input symbol that you're looking at, the system halts, right? But it's possible that you just stay in one state and go to another state and keep doing things, and your system never halts. So an early question was, given the state information for a Turing machine and the contents of the tape, can you stare at those and answer the question, will this machine eventually halt? It's a deterministic question. There's no randomness here. But it's basically like saying, if you look at a piece of C code, can you decide if it's ever going to exit or will it loop forever? That's called the halting problem. And it was studied intensely in the 20s and 30s. And the conclusion was it's impossible to write a program on a Turing machine that solves the halting problem. Okay.
Like if this machine did exist, it would cause conflicts, and thus it wouldn't work like
Yeah.
it's supposed to.
And it's the same thing as the incompleteness theorem that we touched on with systems of arithmetic. So we'll talk about the halting problem tomorrow. We'll look at an outline of a proof as to why the halting problem is impossible to solve. And we'll talk about ramifications if you could solve the halting problem. And then we'll move on. We'll start talking about graph theory. That's our final unit. All right, so turn in your homework if you want it graded today with 5 bonus points. Otherwise, bring your homework tomorrow and turn it in at the beginning of class. And I'll see you then.